If you have a potential, the transmission coefficient for a potential where Z naught is equal to 13 pi over 4. That's a square well of certain depth, and we've represented it this way. Remember, n must be greater than or equal than 2z naught over pi. So this would be 13 halves. And 13 halves means that we can start with n equals 7, 8, 9, and all those. Remember, this n counts which bound state of the infinite square well we are talking about, and the energy that you must use or you're interested are positive energies. So positive energies mean that you have sufficiently large n, and the n that is sufficiently large is 7 in this case. So you can then determine from this formula what is the value of En over V naught. So for example, E7 over V naught turns out to be 0.15976. E8 over V naught turns out to be 0.5147993. And E9 over V naught is 0.91716. So if you plot it, you have here E, or capital energy, over V naught, and you want to plot the transmission probability. And it begins with 0. That was the question a second ago. And then it may reach 1. And it will reach 1 at each one of those values. So if here is 1, 0.15, there will be 0.15, 0.51, and 0.92. So you get this, and here another one, and here another one. So property like that. So that's a typical graph for the transmission probability. It oscillates, and it reaches 1 at several points forever and ever. The amplitude becomes smaller, so it's really overall tending to 1. So these two people we're talking about, Ramsauer and Townsend, they were lived from the 1860s to 1940s and 50s, and they did their famous experiment in 1921. So their experiment was elastic scattering of low energy electrons off of rare gas atoms. So Ramsauer and Townsend, in 1921, they scattered elastically. That means the particles didn't change their identities. You didn't create more particles, just electrons came in and electrons went out. Electrons. And these are low energy electrons. Off of rare gas atoms. So these are noble gases. Their shells are completely filled. And they're rather inert, very unreactive, high ionization energies, no low energy states you can scatter this atom into. So basically, it's a very unreactive atom. And you can imagine it as a very beautiful spherical cloud in which there's electron, there's a protons, a nucleus here, and an electron cloud. So how does this look to an electron? Well, you know from electrostatics that if you have total charge 0 and it's totally spherically symmetric, no electric field outside. So the electron comes in, feels nothing. And as soon as you penetrate this, at any point here, the electric field points in. Or, well, it actually points out, but the electron will feel a force in because the charge in the outside shell doesn't produce any field, but now the protons in the nucleus beat the effect of the electron. So there's a force in that goes in. So basically this is like a deep square well or spherical well representing the atom. The atom can be thought as some sort of spherical well that attracts the electrons. So what these people did were throwing these electrons, and they considered that these electrons scattered a lot when they bounced back. On the other hand, if they continued, if the electrons passed by, they said nothing has happened. So the reflection coefficient for them, the reflection coefficient is a proxy, a good representation for the scattering cross-section. So the reflection coefficient, what they found experimentally was a reflection coefficient R that as a function of energy was very high. And people thought at this moment, okay, these are like particles colliding with particles. The energy shouldn't make much difference. You know, you either collide or you don't collide, and you bounce back or you don't bounce back. And so they thought that this would be flat, but nevertheless, it actually went down enormously, and then it went up again. So they found that for about electrons with about 1 eV, that's very low energy electrons, but they're going pretty fast. And 1 eV electron is going like at 600 kilometers per second. So the reflection was going like this, and they had no explanation why it was so sensitive with energy, and why there would be a funny effect going on that the reflection would suddenly go down and just basically the particles would get transmitted. But if you think of reflection here as continuous line and transmission as dotted line, the transmission that must add to the reflection to be 1 would be going up here and would have reached near 1 at this value of the energy. So the explanation eventually was this effect, that you should do well, and there's a resonant effect in the well, and for some energies, the resonance is such that it allows the particles to just go through and not to scatter. So this had to wait some time because the experiment was done in 1921, and Schrödinger and everybody started doing good work in 1925. And wave mechanics took a while, but eventually it was recognized that basically it's resonant transmission what is happening there. And well, if you want to get the numbers right, if you want to get that EV better, you have to do a spherical model of the finite square well. You have to do a spherical well and do it a little more precisely, but then the agreement is pretty reasonable.